All right, so now we're looking at a rectangular corral that's to be divided into three enclosures, all having the same size as shown below. The total amount of fencing to be used for the outside of the corral and the sides of the enclosure is 500 feet. So we're going to find dimensions of the corral that will maximize the area of the enclosure. All of that said, we're going to go ahead and see, we're looking at that area, right? That's what we want to maximize. So we need a function that's going to be in terms of the area of this enclosure. So the corral that we're looking at. So we have to remember a formula we know about rectangles and area. Well, the area of a rectangle is equal to length multiplied to width. Okay, so that's something that we have to know. That's previous information, it's not given. Okay, we also know that this 500 feet is going to take up all these sides. That's what this 500 feet is. So all of those sides, so we're going to be summing up. So this 500 feet, we're going to do is the sum of all sides is equal to 500 feet. It's another thing that we know, we understand that intuitively. We don't have to be, explain that in full detail. We're actually told that. Okay? So what we need to do is look at what each of these parts are, give them some kind of meaning or the labeling them. So this one here we'll call length. This one will be the width. Okay. It doesn't matter which one you called which. But when we look at the sum of all those sides and we're going to add them up, we recognize that the length and the width, right, there are 4 widths to add up, and there are 2 lengths to add up. So that means we're going to have 2 lengths plus 4 widths equals 500. Notice that they're all divisible by 2, so let's go ahead and divide by 2. So that we have L plus 2W is equal to 250. Then from here, we can go ahead and solve for one variable in terms of another, because when we do functions right now, we're only doing functions for one variable. We're not doing multivariable functions. So we need to just go down to just one variable that describes another one. So when we solve for L, we get L is equal to 250 minus 2W. Now that I have that, notice when I go to the area is equal to length times width, so I write it in shorthand there. This is really, now I'm going to, instead of it just being a formula for area, I'm going to write it as a function in terms of width. So I can replace length with 250 minus 2W, and now times W. I distribute that W to get 250 W minus 2W squared. And then it's here that I can see A and B because I want to maximize. The whole idea here is maximizing. Whenever I see this maximization, that means I'm looking for the vertex. So when I look for the vertex to maximize, means we're looking for that vertex. The vertex then I need to find A, which is -2, and B, which is then 250. So H is equal to -B over 2A. In this case, we are actually finding W. We're finding the width. Okay, because that is our variable of our function. So -250 divided by 2 times -2. So that gets me then 250 over 4, which ends up being 125 over 2. Okay, or 62.5. Now, from here, before I go ahead, I don't like to mess with the decimals because now I need to I found width. That's the whole point here. I found the width that would maximize the area. It wants the dimensions, so both length and width. But I know how to find the length in terms of width. So all I need to do is plug in the value of W that maximizes area. So that means I'm going to have length is equal to 250 minus 2 times then 125 over 2. So those cancel and go to 1. And so I have 250 minus 125. So that equals 125. So that means that the dimensions are, so I have the length, 125 feet, and my width, 62.5 feet. So the dimensions that maximizes the area is 62 feet by 125 feet.